Okay, till now we have discussed type 1 and type 2 filters of linear phase. Okay, so in this lecture let us discuss type 3 filter. So the first condition is antisymmetry for type 3 filter. Okay, and antisymmetry means h of n is equal to minus of h of capital N minus small n, and the length of the filter is what? It is odd. Length means capital N plus 1. If n plus 1 is odd, then what about n? N is an even number. Okay, so therefore n is even and n plus 1 is odd. Now again let us understand this type 3 filter through an example, so that will be easy. So what we did in the type 1, likewise we will take capital N is equal to 8. Okay, so let us take n is equal to 8 as we did earlier for type 1 filter. So to concretize our idea, we took this example. So you have h0, h1, h suffix 2, h3, h4. See, this is a short form notation. Instead of h0 is nothing but h of 0. Okay, so don't get confused. Okay, h5, h6, h7 and h8. Now take this relation. In this, substitute n is equal to 8. Therefore h of small n is equal to minus h of 8 minus small n. Substitute n is equal to 0, h of 0 equal to a minus h of 8. H of 1 is equal to minus h of 7. H of 2 is equal to minus h of 6. H of 3 is equal to minus h of 5. And then h of 4 is a loner term. Okay, so the pairings are h of 0 with h of 8, but they are not equal now. Okay, they are equal and opposite because of antisymmetric. So h of 0 is equal to minus h of 8. Similarly, h of 1 is equal to minus h of 7, and so on and so forth. And h of 4, what do you think h of 4 will be? Because by the definition h of 4 must be equal to minus h of 4, isn't it? So in the formula you substitute. Here n is equal to 4, this is 4, h of 4, and here also minus h of 4. Now this implies what? H of 4 is equal to 0, identically equal to 0. Therefore, the pairings are h of 0 should be equal to h of 8 with a negative sign, h of 1, h of 7, h2 with h6, h3 with h4. h4 is a loner, but now this loner is 0. Therefore, h4 is equal to 0. Okay, so h2 is equal to minus h6, h3 is equal to minus h5, and therefore h4 is identically equal to 0. Okay, so the axis, therefore this is the axis of symmetry. Okay, and therefore in general one can write h of capital N by 2 is identically equal to 0. Okay, and this introduces further restrictions, okay, that we will see now. Okay, now let us try to find out the frequency response. Now first to find out the Fourier transform, z transform of this to get the transfer function. So h of z is equal to h naught plus z to the 0 plus h1 z to the minus 1, h2 z to the minus 2, h3 z to the minus 3 plus h4 z to the minus 4 plus h5 z to the minus 5. Am I right? Yes. Plus h6 z to the minus 6 plus h7 z to the minus 7, then plus h8 z to the minus 8. Now we said H4 is identically equal to 0, you can leave it. And then H3 is the same as H5 is equal to minus H3. Look at here. H3 will be equal to minus H5, or H5 is equal to minus H3. Therefore, here I can write, let me put some other color, minus H3. And then this H6 is equal to minus H2. And then this H7 is equal to minus H1. And then this H8 is equal to minus H0. Okay, H7 is the same as minus H1. Therefore, I will have this term. H8 is the same as minus H0. Therefore, I will have this term. Isn't it? So, therefore, this is reduced as H0 z to the power 0, or I can say 1 minus z to the minus 8 plus H1 z to the z inverse minus z to the minus 7 plus H2 z to the minus 2 minus z to the minus 6 plus H3 z to the minus 3 minus z to the minus 5. So, what is the next step? We need to find out the frequency response. Okay, and we don't have H4 because H4 is a middle sample and that is identically equal to 0. Okay, now before we go to the next step, like finding the frequency response, suppose we change our z inverse to z. What do you think? What will you get? Then how can we regain h of z from h of z inverse? This is h of z. Replace z by z inverse or z inverse by z. Therefore, you will get h of z inverse. Okay, simply you multiply z to the minus 8 by h of z, but the signs are interchanged. Okay, for example, if you take this guy, what do you think this will be? Z to the minus 8 h0 1 minus z to the minus 8. Okay, 1 second, I'm sorry. Take this portion alone. This is h0 1 minus z to the minus 8. Okay, now replace z by minus z. Therefore, h0 times 1 minus z to the by 8, z inverse, and then multiply z to the power 8 times h0 of 1 minus z to the power 8. This is going to be h0 times z to the power multiply by minus 8. Okay, z to the minus 8 minus 1. This is the same as minus h0 times 1 minus z to the minus 8. Okay, now compare this and this. What do you think? Only there is a negative sign here. Okay, so I have taken the first term, this term. In this term, I multiplied z by minus z inverse. I got this expression, and then I multiplied by z to the minus 8. Then I got this one. Now compare this guy, and this guy. What is the difference? There is a minus sitting here, this minus. Okay, so the sign only changes. Therefore, this I cannot write like this. So h of z is equal to z to the minus 8 h of z inverse, and you put a minus sign here. Okay, so this is wrong. Okay, don't take this one. So this is a condition. Therefore, in general, I can write h of z is equal to minus z to the minus n h of z inverse. Okay, this is a general formula. This you can prove from this. Okay, you can take the first term, second term, third term, and fourth term. Replace this all this all these terms. Replace z by z inverse or z inverse by z, and then you multiply by z to the minus 8. Then the same expression will get back, but all these expressions are multiplied by minus 1. That's what we are trying to say here, nothing else. Okay, so this is the only difference, minus sign. In antisymmetry, a negative sign comes. This negative sign comes. In antisymmetry, a negative sign comes. If you recall from type 1 and type 2 filters, h of z is equal to z to the minus n h of z inverse for type 1 and type 2 filters. But for type 3, there is a minus symbol. This minus symbol comes because of the antisymmetry. Okay, so for types 1 and 2, symmetrical impulse response. Okay, therefore this sign is, if you look at here, there is a plus sign, positive sign, but here there is a negative sign. That's it. And this is where further restrictions on type 3 comes. Now let us continue. Let us find out the frequency response. So let us find out the frequency response. As I said, how will you find out frequency response? Replace z by e to the j omega. Therefore this becomes h naught times 1 minus e to the minus j8 omega, isn't it? Plus h1 times e to the minus j omega minus e to the minus j7 omega, plus h2 times e to the minus j2 omega minus e to the minus j6 omega, plus h3 times e to the minus j3 omega minus e to the j minus 5 omega. And now in this you take e to the minus j4 omega commonly outside, e to the minus j4 omega within the bracket, h naught times e to the plus j4 omega minus e to the minus j4 omega plus h1 times e to the plus j3 omega. Is that right? Yes, minus e to the minus j3 omega plus h2 times e to the plus j2 omega minus e to the minus j2 omega plus h3 times e to the plus j omega minus e to the minus j omega. Okay, now what is this? If you use Euler's identity, then this is sine omega. Okay, sine 4 omega, but the multiplying factor is 2j. Therefore this is equal to e to the minus j4 omega multiplied by 2j h naught sine 4 omega plus 2j h1 sine 3 omega plus 2j h2 sine 2 omega plus 2j h3 sine omega. That's it. This is what you will get it. Okay, so this is a final expression. Okay, so what I did, I just put z equal to e to the j omega, and then I take e to the minus j4 omega commonly outside, and then finally I got this expression. So this j factor comes because e to the plus j theta plus e to the minus j theta by 2j is the sin theta. So what you do, you divide by 2j and multiply by 2j, and here also divide by 2j and multiply by 2j. So this 2j factor appears with the h1. Okay, so this is your h of e to the j omega. Okay, so here I have the factor of j, and this j term, as I said, it introduces a phase shift of pi by 2. Therefore, this I can write as h of e to the j omega is equal to e to the minus j 4 omega. You take this j commonly outside, everywhere the j term is there, you can bring outside of this. Therefore, that j gives e to the j times pi by 2 phase angle, and then you can write rest of the terms, or I will write out one more step so that you can understand very clearly. You can write j times 2 times h naught sin 4 omega plus 2 times h1 sin 3 omega plus, I can take 2 also, no problem. Okay, and then h2 times sin 2 omega plus h3 times sin omega, like this. And this j term gives the phase shift of pi by 2. Therefore, e to the minus j 4 omega plus e to the j pi by 2, and the rest of the terms. Okay, now in general, how can I write? This 4 is nothing but 8 by 2, that is n by 2. Therefore, the general expression is e to the minus j n by 2 omega e to the j pi by 2, and this whole expression I can write in the compact form as h of capital N by 2 minus n sin of n omega, where n goes from 1 to n by 2. Take again, substitute n is equal to 8 here in this expression, and substitute n is equal to 1, 2, 3, 4, and then you get back this expression. Therefore, this is the general expression. Now, what is a phase shift? Phase shift phi is equal to, look at here, minus j 4 omega plus pi by 2 plus some phase angle beta. So in general, instead of writing 4, I can write minus j time, sorry, this j term will not come, I am sorry, I am writing the phase right. So instead of writing 4, let me write minus n by 2 plus pi by 2 plus some phase angle beta. This phase beta comes from this guy, from this summation. Okay, possibility of this real time. See, this is a real term, right? Isn't it? Sine term is a real term, real function, but which is a pseudo magnitude. Okay, this real term can also have a change of sign, and therefore you must admit a beta here. Now this is my phase phi, minus n by 2 times omega. I forgot to include omega here, minus n by 2 omega. Let me write it clearly. Minus n by 2 omega plus pi by 2 plus beta. Now, as I said, what is the group delay? Tau suffix g of omega is equal to n by 2. Anyway, this pi by 2 will become 0. Negative gradient of phase is nothing but group delay, that is n by 2. Okay, therefore negative gradient of phase is plus n by 2. Okay, and the important point one must notice is that the transfer function h n of z is not equal to z to the minus n h n of z. There is a minus sign here. So as far as zeros are concerned, zeros are occurring in reciprocal pairs, no problem. But you notice now for type 3, n is even, isn't it? N is even. Therefore, h n of 1 is equal to minus h n of 1, which means Hn of 1 must be equal to 0. Similarly, Hn of minus 1 is equal to minus Hn of minus 1, which means Hn of minus 1 is also 0. Is also equal to 0. Okay, in terms of zeros, obviously we have zeros at plus 1 as well as minus 1. I have two zeros. The zeros are located at plus 1 and minus 1. So in the plot, this is omega is equal to 0 and this is omega is equal to pi. That means z equal to 1 and z equal to minus 1. So the magnitude is 0 here. But low pass filter, I need magnitude of unity magnitude here. For high pass filter, I need unity magnitude here. Therefore, low pass filter you can't realize, and high pass filter also you can't realize using this type 3 filter. Because for type 3 filter, the magnitude is identically equal to 0 at z equal to 1 and z equal to minus 1. Z equal to minus 1 corresponds to omega equal to pi. Z equal to minus 1, z equal to plus 1 corresponds to omega equal to pi. That means what? This Hn of z contains two factors. One factor is 1 plus z inverse and another factor is 1 minus z inverse and multiplied by some polynomial h1 of z, some other transfer function. Now the next question is this h1 of z a linear phase? Yes, it has to be. Okay, there is no alternative, because this is a linear phase and this also has a linear phase. Why is it linear phase? Because it gives a constant delay. How will you find out? Replace z by e to the j omega and then you'll come to know. And this also has to be linear. Okay, so from linear phase, this is a linear phase. Linear phase, you are subtracting this linear phase and this linear phase from the rest, from this h1 of z. So therefore this h1 of z, the rest must be a linear phase, otherwise the sum cannot be a linear phase. So h1 of z is also a linear phase. It contains other zeros which occur in reciprocal pairs. Now what about this 1 plus z inverse 0? So why didn't it occur in reciprocal? Because reciprocal of plus 1 is plus 1 itself. Reciprocal of minus 1 is also minus 1. Therefore they can also occur singly. But in h1 of z, the rest of the function may not contain another 0 at plus 1 or minus 1. Okay, I said may not. Why not? It may also contain multiple poles at z equal to 1 and multiple poles at z equal to minus 1. For example, I may have 1 plus z inverse whole square and 1 minus z inverse whole square, whatever it is. Therefore, h of z is in the form of 1 plus z inverse times 1 minus z inverse times h1 of z. So it must have at least 1 0 at plus 1 and as well as 1 0 at minus 1. So in the plot, 1 0 here and 1 0 here, so it is a unit circle. Therefore the only thing that you can do in type 3 is band pass filter, that's all. So here the magnitude is 0 and here also the magnitude is 0. So for low pass filter I need unity magnitude at omega is equal to 0. For high pass filter I need unity magnitude at omega equal to pi. For band stop filter also I need unity magnitude at omega equal to 0 at omega equal to pi, like this. For band stop filter, for low pass filter like this, for high pass filter like this. Okay, that means I need unity magnitude at these points. But unfortunately my type 3 filter has 0 response at omega equal to 0 and omega equal to pi. Therefore I cannot realize low pass filter, then high pass filter and then band stop filter using type 3 filter. The only filter that can be realized by type 3 filter is the band pass filter, because the band pass filter response will be like this. This is omega is equal to pi, and here omega is equal to 0. Therefore, no problem. So comfortably I can realize band pass filter. Okay, so that's it about type 3 filter.